Okay, let's focus now on depicting the function, the second function in this list, right? This one. Um, there's a problem to depict this function is the fact that we have absolute values. So what we are going to do is to describe this function in all possible regions according to the sign of the arguments of these absolute values. You see, there is a change of sign of the x on the left and on the right of 0, right? And that makes a different definition of the absolute value on the left and the right of 0. And here is the same with 1. So we have three regions. The first region is x negative, right? So x is smaller than 0. The second region is x is between 0 and 1. And the third region is x is larger than 1. Well, we will worry later about what happens at the borders of these three regions, right? But for time being, I'm just distinguishing these three regions to describe the function in them. So in the region 1, the function f is what? Well, x is negative, so in the denominator we have minus x minus 1, by definition of the absolute value. And same here, right? Okay, we have 1 over x minus 1. It's got a minus sign, so what we do is change the sign here, and then we have this, okay? So this is the same as minus 1 over x plus 1 plus 1 over x minus 1. And if we reduce this to a common denominator, we have minus x plus 1 plus x plus 1 divided by x squared minus 1. You cancel the x, and then you get 2 over x squared minus 1, which is a very compact form to represent this function, right? And the second, in the second region, what we have is this one here, the argument is positive, this one is negative, so what we have is this is the same, but this changes sign, so what we have is 1 over x minus 1 plus 1 over x minus 1, which is twice the same function, so it's 2 over x minus 1. And in the third region, this piece is equal to this, so 1 over x minus 1, okay? However, this one, now the argument becomes positive, so it's got this form. Both are the same, so the difference is equal to 0. So we have a function f to represent, which is defined in three pieces. First piece is 2 over x squared minus 1, which is valid when x is negative. And of course, x cannot be negative 1, because at the negative 1, the denominator is not defined, right? It's also not defined at 1, but 1 is outside this region, so we don't care about that. In the second region, the form is this one, okay? That is x larger than 0 and smaller than 1. Okay, at 1 the function is not defined because there is a 0 in the denominator, but at 0 there's no problem. Right here the function reaches the value negative 2, and it's the same value that it reaches if we evaluate this one at 0, which means the function is continuous, so it doesn't matter whether we include the 0 here or here, the value is the same. And finally, the function is defined at 0 when x is larger than 1. Alright, so first thing that we know about this function then is that the domain of f is r minus plus and minus 1, right? The 2 points where the function is not defined. Otherwise, it's got this definition in three pieces, right? Okay. Now, to proceed, well, first, since the function is singular, because the denominator is 0, at the point negative 1 and at the point 1, it's got two vertical asymptotes. So there are two vertical asymptotes, which are x equal to plus or minus 1, right? And on the right hand side, so for x positive and large, the function is just constant. So obviously there is a horizontal asymptote, which is the function itself. And on the negative side, well, if you calculate the limit when x goes to minus infinity of the function f, well, you have to take this form, and clearly the limit of this is equal to 0. So there is a horizontal asymptote. Which is y equal to 0, right? So these are two pieces of evidence about what the function f looks like. And the next thing to do, of course, is to decide whether the function grows or decreases or what. So let's calculate the derivative then. Well, we have first, in the first region, the function is defined like this, right? So we take here the derivative, we get 2 divided by the, minus 2 divided by this square, okay, and then multiply by the derivative of this, which is 2x. So what we have is minus 4x over x squared minus 1 squared, right? This is valid when x is negative, but of course different from -1, okay? Then if x is between 0 and 1, then we have this other definition, and the derivative of that is just minus 2 over x minus 1 squared. And this is valid when x is between 0 and 1. Well, we have to exclude the 0 for time being because we don't know what happens at 0, right? But it has to be separate, taken care of separately, because the derivative on the left and on the right might be different, and then the derivative will not be defined. Actually, that is the case, because you see the derivative on the left of 0 is equal to this evaluated at 0, which is 0, whereas the derivative on the right of 0, so calculated here, is, well, you put here 0 here, the denominator is 1, so it's -2. So it's not differentiable if it's not differentiable at x equal to 0. The function is continuous there, but has no derivative, right? Because the slope of the two curves are different on the left and on the right. Okay. And finally, in the third region, the function is of course constant equal to 0, so the derivative will be 0 as well. So that is the derivative of the function, which means that f prime is positive when x is negative, right? Excluding, of course, -1. Okay, it's positive because x is negative, and you have a minus here, and the denominator is positive, right? So the function grows here, and in the region 0, 1, the derivative is negative, right? Because the denominator here is positive, so we have a negative. So in this region it decreases, and of course it's constant. Derivative is constant on the right of 1, so for x larger than 1. All right, we can collect all these pieces of evidence, and then we have a representation of the function, which is given by this plot here, right? So this is what the function looks like. As I said, the function is the function grows in the negative side up to 0, right? It's got two vertical asymptotes, okay, so it diverges here, but it's still growing, right? It has when x goes to minus infinity, it approaches y equal to 0, which is a horizontal asymptote, right? And if you calculate what is the derivative at this point, is 0, which is represented by the tangent, the horizontal tangent that you have here, right? By the way, the value of the function itself at 0, which decides whether this point is here or up here, is calculated just substituting here, and as we have seen before, this is -2, right? So this function is -2, which means that it stops here. It grows up to this point, and it reaches this point with a horizontal slope, like this. Then we go to the positive side, and in the positive side, between 0 and 1, the function decreases. There's a vertical asymptote here, So it decreases this way up to the vertical asymptote, so getting closer and closer. And the derivative here is -2, which is the slope of this straight line here. So that is the tangent on the right. And as you can see, this point has two different tangents, horizontal on one side, -2 on the other side. So this point here is not differentiable. The function is not differentiable there. And finally, in the last region, which means x larger than 1, the function is constant equal to 0. So this is the representation of this function.